So the third theorem, or theorem number 3, is circular frequency shifting. Circular frequency shifting. And here we have phase shift in the time domain of the sequence x of n, which will give dft of shifted version of x of k, circular shift actually, middle n. So we can conclude from theorem 2 and 3 that the circular frequency shifting and circular time shifting, that if you have a shift in time, you have a phase shift in frequency, and you have, on the other hand, if you have a frequency shift or a shift in frequency, then you have a phase shift in the time domain. Okay. Theorem number 4 is a very important theorem. It is the endpoint circular convolution. Okay, and here yc of n, the circular convolution resultant of x of n convolved with h of n. So you have a circular convolution of length of n point. This has the dft of x of k times h of k. Okay, so which is this one here is equal to y sub c of k. All right. In a block diagram, we can demonstrate this in the following manner. If we have endpoint dft, and this block diagram or system, we apply x of n as an input for it, and we have another system as endpoint dft also, a replica of it, apply h of n as an input to this system. So you will get here x of k, and here you will get h of k. Take those two and multiply it together. You get here x of k times h of k. All right, so those are the yc of k. Now, if you take this to a block diagram or a system with endpoint inverse dft, so you will get here yc of n. And this is one good way of implementing the circular convolution using the DFT. So you can do the circular convolution in time domain, or you can also do it in frequency domain as shown in this block diagram. Okay, the last theorem that we are going to discuss today is the Parseval's relation. And the Parseval's relation stated that summation from n equals 0 up to n minus 1 of the magnitude of x of n squared is equal to 1 over n, the summation from k equals 0 up to n minus 1 magnitude of x of k squared. So Parseval's relation is related to the energy of the sequence. You can calculate the amount of energy of the sequence either in time domain by this form or in frequency domain by this form. Please be careful. Parseval's relation is equality. It's not a Fourier transform pair as shown here. Those here are Fourier transform pairs. Parseval's relation is an equality. So you have equal sign, not a double arrow as in the Fourier transform. Okay, so you can find the energy in time domain and or you have an alternative way to find the energy using the frequency domain DFT of the sequence. Okay, let's take an example here and take x of n equals to 1, 2, 3, and 4. And actually, we know x of k from previous example in this session. We have x of k equals to 10 minus 2 plus j2 minus 2 and minus 2 minus j2. So we know x of n and we know x of k. We will find the energy of the discrete time signal using Parseval's relation. The first way, we will use the time domain. So we have the sum of x of n magnitude squared from n equals 0 to 3, and this is equals to 1 squared plus 2 squared plus 3 squared plus 4 squared, and this is equals to 1 plus 4 plus 9 plus 16, and it's equal to 30. Okay? Okay. Using the frequency domain, so if you use the frequency domain, we will have to use 1 over 4 summation magnitude of x of k squared from k equals 0 to 3, and this is equals to 1/4 of. Okay, going back to the signal of x of k in frequency, the first one is 10 squared plus the second one is the second element. As you see here, you can see here that the second element is complex, so we need the magnitude square. The magnitude square of this complex quantity here is minus 2 squared plus 2 squared without the square root. The third element is minus 2. Its magnitude is 2 minus 2 squared. And the last element also, if you look here, the last element is also a complex quantity. Its magnitude is minus 2 squared plus minus 2 squared. So this is the whole thing. The 1/4 100 plus 4 plus 4 plus 4 plus 4 and plus 4. So this is equals to 120 divided by 4, and this equals 30. So you can see that both answers are the same, and this demonstrates the Parseval's relation for the DFT problems. Thank you very much for listening, and I hope you enjoyed my lecture.